Hi, so this is CSM 16A Spring 2018 Worksheet 6, problem number 2. So let's get started with part A, where we're seeing what happens with resistors in series. So let's start out by drawing resistors in series. So the way we can do this is we have node B, and we have a wire connecting this resistor to node A. And we have some current I. And this is resistor 1 and resistor 2. So now we know, first off, we know that this current here is the same as the current here because it's all one wire. And we are looking to find the equivalent resistance, so we can denote that by Req. And if we know that the voltage drop between node B here and node A is V, then we also know that the voltage drop between resistor 1 is V1 and the voltage drop between resistor 2 is V2. We can write this total voltage drop V as V1 plus V2. So now, using Ohm's law, we can say Req is equal to V over I, where V is the voltage drop from node B to node A. And plugging in our V1 plus V2 into this equation, we get Req equals V1 plus V2 over I, which is equal to V1 over I plus V2 over I. And from this relation, we know that V1 over I is R1, and that V2 over I is R2. So then we can write Req equals R1 plus R2. Another way to think about this is when you connect two resistors in series, we see that, so here let me draw it out again. So we have resistors here, and we have R1, R2. So if R2 equals R1, and we can just say that the resistance value is R, we know our formula is R equals PL over A. And like visually you can see that, okay, this whole length here is double the length of one resistor. So our Req equals 2PL, or we can write it out better like 2P times 2L over the same cross-sectional area A. And this is the same thing as 2PL over A and 2R. So intuitively, we can see that our equivalent resistance for resistors in series is greater than the original resistance of one of the resistors. Okay, so for part B, we want to see what happens when we connect two resistors in parallel. So let's start by drawing this out again. So here we have our node B, and this splits into here, and that connects to node A. Then we have this, and we can label these once again R1, R2, and we start with some current I, and since it splits here, we have some current I1 going into resistor 1, and some current I2 going into resistor 2. So now that we have our two resistors in parallel, we know that by KCL, we know that I equals I1 plus I2. So similar to part A, we need to see like how can we use this relation. So we have our formula, once again, by Ohm's law, that Req equals V over I, where V is the voltage drop from node B to node A. And this can be rewritten like 1 over Req equals I over V. And then we plug in our relation for I into this equation. So we get I1 plus I2 over V. And this is I1 over V plus I2 over V. And this is the same thing as 1 over R1 plus 1 over R2. So this gives our final relation of 1 over Req equals 1 over R1 plus 1 over R2. And we can write this for Req as 1 over R1 plus 1 over R2. Another way to think about this is that when you're combining these resistors, and if you like draw boxes around it, then when you combine them, you're combining them by the side, so you're combining it here. And this increases the cross-sectional area. And looking at our R equals PLA formula, if we increase the cross-sectional area, then we're increasing the denominator, and our equivalent resistance will be less than our original resistors. Going back to this equation, our general form is REQ equals 1 over R1 plus 1 over R2 plus 1 over Rn for n resistors. And that's the end of part B. Okay, so let's move on to part C. So first off, our goal is to mark all the nodes in this circuit here. So what is like a property of a node? So the main property that we should keep in mind is that the voltage is the same across a node. And then the way I like to think about it or go about it is you start at a point on a wire, and you just keep following that wire in all directions until you hit a component. So in this case, we go here. Oh no, we hit this 2K resistor, so we stop. And then now we can move in this direction, and then this direction, and now, oh no, we hit another 2K resistor, so we stop there. Then we move the other way, and we hit a 4K resistor, so we stop there. And that's the end of our node, because we can't go in any more directions. And by convention, you label nodes using the alphabet, so let's label this node as node A. Now we start on the other side of this 2K resistor, and we just keep following our wire until we hit another component. And then here we hit this 2K resistor, and that's the end of our node. So we can call this node C. And then here we start at this point and follow the same trick, and we hit a resistor there, then we move up, hit a resistor there, hit a resistor there. That's the end of our node, and we can call that node B. And then lastly, we follow this wire, and we hit our component there, so we're done, and we label it node D. And that's the end of part C. Now for part D, we need to label which nodes are two nodes and which nodes are multi-nodes. So in the problem, it says that two nodes are connected to only two components. Multi-nodes are connected to 3 or more components. So now let's see what nodes, or how many components each node is connected to. So A is connected to 1, 2, 3. 3 components. B is connected to 1, 2, 3 components as well. And then now let's look at C and D. So C is connected to 1, 2. And D is connected to 1, 2. 2 also. And so C and D are two nodes. A and B are multi-nodes. Now let's move on to part E. So resistors that are connected to two nodes are considered to be in series. Now let's try to redraw this circuit and find the two and multi-nodes again after redrawing this circuit. So knowing that two nodes are considered to be series, or resistors that are connected to two nodes are considered to be in series, we have, going back to part C, we have this 2K resistor is in series with this 2K resistor, and this 2K resistor is in series with this 2K resistor, because C and D are both two nodes. So combining these using our equation from above, where REQ equals R1 plus R2 plus Rn for n resistors, we know that the REQ for C, for node C, is 2 plus 2, which is 4K ohms, and the REQ for part D, or for node D, is 2 plus 2 equals 4K ohms again. So redrawing the circuit, we can combine those resistors into one resistor of 4K ohms each. So we have our node A, we draw this, can draw this like this, and then we have one resistor here, our original resistor, and then our other resistor, and then we just keep going like this, and then we end at node B. And we draw these back in. And these are all 4K ohms resistors. And there we go. That's how we redraw the circuit. Okay, now let's look at part F. So just for convenience to look at, I redrew the circuit that we came up with in part E. And so now let's write out the two nodes that each resistor is connected to. So let's call this R1, R2, R3. So R1 is connected to nodes A and nodes B. R2 is also connected to nodes A and nodes B. And R3 is connected to nodes B and nodes A as well. And that's the end of part F. All right, moving on to part G, we have the fact that if two or more resistors are connected to the same two nodes, they are in parallel. So from part F, we see that R1, R2, and R3 are connected to node A and B. So this means that they are parallel. So using our handy-dandy formula from part B, we have our R equivalence is 1 over R1 plus 1 over R2 plus all the way to Rn for n resistors. And plugging in our values, we have 1 over 1/4 plus 1 over 1/4 plus 1 over 4. And this gives us 1 over 3/4, which is equal to 4/3 K ohms. And so all these three resistors, all R1, R2, and R3 can be compressed to some equivalent resistor of 4/3 K ohms. And just as a tip, if you have n resistors of equivalent resistance and they're in parallel, their REQ is R over N for N resistors. And that's the end of part G and problem 2.